With the recording. Hey, kind of a new procedure, so I got to keep my eye on the participants. Right now, we're missing about 7 people. There's one more, admit. What's happening, I guess, with Zoom is, as opposed to photo bombing, there have been reports that Zoom has had to react to about people Zoom bombing. And so we'll be holding a class. There was a story on the internet, it was on Facebook, so it has to be true, where a guy was defending his dissertation for his PhD, and the entire faculty's there. They're doing it via Zoom, and somebody, and I guess he had relatives there, family watching, maybe even kids, and then somebody photobombed him, hacked their way into his Zoom site, started leaving foul language stuff on the whiteboard, and making vocal comments that were profane, things like that. And so Zoom has upgraded its security procedures. One of them is, if you drop out, you have to go in with the password that should be in the email. Okay, so that's one of them, and I have to admit you into the class. And so far, I guess we've got, looks like 15, still missing 4 folks. I'll have to keep my eye on it. Hopefully I won't miss anybody who's trying to join the class here. That would be a mistake, but we always get punished for the bad people. Isn't that the way it is? Zoom has to implement these procedures because of just a few bad apples. Internet security is all about, if we all just could get along and use it correctly, we wouldn't have any of that stuff. And we can all buy much less expensive computers because the technology would be much cheaper. Any event, let's move on. I did want to talk a little bit about some administrative things that I'm sure are key in everybody's mind. Milestone day today, worksheet 30. We're going to talk about the relationship between magnetic fields and electric fields, actually really between a magnetic field and electric potentials, electromotive forces, but they show up as they're related to electric fields, and we'll talk about that. So we've been talking about magnetic fields for the last 2 weeks, I guess, maybe a little over. We're going to shift over and we'll be talking about both electric and magnetic fields today and how one can cause the other. Let's see. So worksheet 30 is sitting right there. It's due, let's see, today's the 13th, 14th. I made it due Thursday because I don't want it to interfere with the midterm. And if you're looking here, these are the resources I think you might find useful. At the top of each section, each chapter, and I sometimes double up a chapter, is my lecture notes, my PowerPoints. I made them into PDFs, so all the equations are there and very readable. Okay. Then there's the worksheet. Hold it. Oh, that's the lab. Then there's the worksheets. Okay. And then there's my solution to the worksheet, my solution to the worksheet. And so, for the recent ones, I guess you have your solutions because you posted them and you saw my marks as I marked them up. But for all the rest, you should always see my solution there. And of course, there's probably some overlap between exam questions and worksheet questions and homework questions, and your mastering and homework assignments are still there. So this is your resource. Obviously, the list right here, a lot of good material here. You find a problem, you want to do a Ohm's law problem right there, go to the Ohm's law worksheet, see if there was a similar problem on Ohm's law, see how I solved it, compare that to how you solved it, get it right this time. There's some Kirchhoff loop equations, and it's for series and parallel circuits, how to do all that kind of work. There's the worksheets for that. Now, on the subject of the exam, I do want to show you that here really quick. So I'm going to stop sharing this. Stop that share. And I want to now, is anybody waiting to get in here? Yep, there's somebody waiting to get in. Yeah, one of the things I'd request, please try to be a couple minutes early for class, since I do have to push the admit button to let everybody in. And, I suspect whoever that was waiting for 2 or 3 minutes there while I was talking. So let me share you my, yeah, there it is, another Google Chrome screen. And this is kind of the exam template. I'm in student view right here. So this is what it should look like to you. You can see it doesn't become, I don't think you can see this right now. I was going to activate it sometime this afternoon. I think it's scheduled to activate tonight around 9:30 in the evening. It's due Wednesday at the start of class. Okay, and you'll notice there is a no credit for late work. There's 25 items. And now let's look right here at the points for each item, and you'll see they kind of vary. There's 2-point problems. They're usually a single equation, maybe two you combine together to get an answer. Some of them, they're a little more complex, 3 points for it, but not a whole lot more. The 1-pointers are generally conceptual problems or very trivial examples. But then you get down here and you see problems 9 and 10 right here, 7-pointer and a 6-pointer. There's 4 like that. Okay, so the majority of the exam, 21 of them are either single point, 3-point, or 2-point problems. But there was a couple 6-pointers. There's another one right there, number 20, and then 24 is a 7-pointer as well. Right, total I think of 65 points. My understanding, and if this is an issue, let me know. You can start the exam, leave it, and come back into the exam. If there's an issue with that, please let me know. Of course, remember it is mastering, so different people have different problems. That shouldn't be an issue, of course, because you can't talk about the exam anyway. But do understand your numbers are likely different from the other person in the class. And so there probably is very often no value in talking, but of course we wouldn't do that anyway. You can use any resource you want. If you've got your paper textbook at home, that's certainly available. If the only textbook you have is the one that's in mastering, my recommendation would be to go to Vital Source. Vital Source is an electronic textbook, and that way you can have that open in, say, another browser like Firefox, Foxfire. I always get that backwards. It is Firefox. You can have that the textbook open in one browser window and be taking the exam in another browser window, say Chrome or Safari, and you can jump back and forth. I like to have a book open in front of me, but the next best thing is to have 2 windows open, one with the book, one with the exam, or one with Canvas and looking at the worksheet problems, and another with the exam. If you've got things in paper, of course, then you're just flipping in a notebook perhaps, or through a stack of papers. And that's the exam. Are there any questions on that before I get moving on today? All right. Hopefully not that big a deal. Do your best on it. You can see one try, right? Single try is the grading policy, I guess. Where's it? Tries per question is 1, and some credit is lost for an incorrect answer. Yes, that's true. Okay. Late, you can see, receives no credit. So please get it done tomorrow, sometime during the day. Anytime's good for you. You can get it done tonight if you want. I'll be watching. And if there are any technical issues, you lose the internet because you're down in North Carolina and you don't have power. Of course, we'll have to work around that. I hope everybody's safe. I saw there was some pretty bad weather in some of our southern states, Georgia, South Carolina, North Carolina. I'm hoping nobody's down there, and we're doing better. All right, moving on here.
Professor,
Yes,
Professor,
go ahead.
how long do we have to take to do this, or
As
can we just take the
much
entire
time
day?
as you need. There is no time
Well,
limit. Okay, you just have to have it done by all 25 questions completed by class on Wednesday. So by 9:30 on Wednesday, have it finished. And you, like I said, you can take 3 hours, 4 hours if you want. I think it should probably take you about an hour and a half to do it. But that there's a big difference there on, do you know the equation? Do you know the concept? Or do you have to go study in order to do the question? If that's the case for all 25 questions, it could take you 4 or 5 hours, I suppose. But that's fine. Just do it. No limit from my perspective. It's just how much time you can spend on it. But it has to be done Wednesday, 9:30. Okay? Does that answer your question? All right. I'm going to stop sharing here. And I guess we'll go to, all right, well, I'm not seeing that. All right, there's that. And so, well, that's awful. I don't see PowerPoint up here to be able to be shared. So let me stop for a second, get rid of you guys, at least minimize you guys. Hold on to that. I hate to have to share. Let's close that one out. Close that one. It's PowerPoint being difficult. That's what the problem is this morning. All right, so let's go back to PowerPoint. Let's close that one. And let's come up with this one. Okay, that's what we're talking about, Faraday's law today. And flux. And now let's try to share that with you. There we go. Don't ask me why I had to close 2 PowerPoint windows in order to share this with you. Hopefully you're seeing my PowerPoint window right now. Did that take? Stop the share. Let's do it one more time just because I don't see the green box around it. Share. All right, and I'm going to go to full screen right here. And, you know, we repeat these, come on, go to full screen. There we go. We repeat these quantities in physics over and over again. We haven't talked about flux for a long time, but I told you, I think back maybe in February, when you talk about electricity, it's really kind of more of an adjective than a noun. We want to talk about like electric fields, electric forces, electric fluxes, electric potentials, electric potential energy. So it's a modifier. And the same thing exists for magnetism. We had magnetic fields and magnetic forces. And it's interesting, there is such a thing as a magnetic potential, equivalent to the V for electricity or the electromotive force for electricity. We just don't study it in an introductory class, but you future physics majors, you'll see it again. The problem is it's a vector and it's a little bit complicated, but we have a potential associated with magnetic fields. But we absolutely have a flux associated with a magnetic field, and that's going to be the highlight, the central feature of Faraday's law, which relates magnetism and electric fields. And I just want to remind you what our definition of electric flux was. In the most general case, where the electric fields are variable in both direction and magnitude, that's why I drew them of different length and in different direction, we find the dot product between the electric field and an area, and we multiply by the cosine of theta. So that's what the dot product involves. The problem here is, I guess, that you might have multiple electric fields at various points on an area, different values of electric field at different points on the area. So you might have to break the area up into little mosaic pieces and sum up the flux from each mosaic piece. And I can envision maybe 6 or 7 little mosaics here, and I add up the electric field times the area to get the flux from each one, sum them all up and get an electric field. And of course, if you've studied integral calculus, you recognize that in the limit of a very, very small area, to ensure that the electric field is constant over that area, that sum becomes an integral. It becomes just adding an infinite number of little areas multiplied by electric field. And so that's what we wrote. Now, I don't think we ever had to do a problem where we did that. In most cases, it is sufficient to think about an electric flux. Come on, pen, you're supposed to be there. To think about an electric flux, symbol phi, subscripted E, because I'm about to talk about magnetic flux, as just a field, which we'll assume to be constant in most cases, times an area, times the cosine of the angle in between the field and the normal to the area. Because if you make that guy a vector, the area vector, its direction is always normal to a plane. Every mathematician will tell you that. Okay, magnetic flux is going to work exactly the same way. If you notice, I changed what used to be B, E to a B, from an electric field to a magnetic field right here, and I subscripted with a B, which you'll sometimes see me be inconsistent, and I'll subscript with an M for magnetic. But in exactly the same way, whenever possible, we're going to talk about a magnetic flux, like through this yellow area right here, which is just B times A times the cosine of theta, as opposed to E times A times the cosine of theta. All right, units. If you think back to electric flux, which was field times area, okay, so E times an A, I guess it would be Newton per Coulomb, right? And then times a meter squared, and that's it. Newton per Coulomb times a meter squared. I've often thought that magnetism researchers back in the 1800s, early 1900s had bigger egos, perhaps, because they seem to name everything after each other. And so in this case, I guess I got a Tesla, right? I got a meter squared, and then of course cosine of theta has no dimensions, and we don't leave it as Tesla meter squared. We call that a Weber. Okay, so a Weber is 1 Tesla, which is an awful big magnetic field, as you probably come to realize, times a meter squared. We rename it a Tesla. And of course, sometimes you'll see people talk about magnetic fields then instead of Tesla as Webers per meter squared, and you might find that in some of your reading, probably in another discipline. Most physicists will revert to Tesla, but you will see in some older literature magnetic fields being described as Webers per meter squared, because they're taking the flux and dividing through by the area and assuming they're perpendicular. Okay, so that's flux. I want to escape out of this for just a second, and I want to go discard my ratings here. And I want to go over and share with you a website. Actually, it's not a website. It's an animation. And so let me share that instead. Come on, Zoom. Where are you? All right. You know, they move things around on me in Zoom, which is always troublesome. Oh, there it is. They put it up there now. Okay, so I'm going to stop the old share, and it moves it back over here. Go figure. And then we're going to share with you, not the desktop. Yeah, that Google Chrome. Nope, the other Google Chrome. That one. There we go. All right, and hopefully you're seeing a field. It turns out to be a magnetic field, and you only know that because it says magnetic field right here. It could just as easily be an electric field. And then I have some area right here, and you can see there's the normal, the red vector to the area. And right now, to calculate the magnetic flux here, we're just taking the magnitude of that magnetic field. And if you take that side of that loop, it's a square loop, you square it, so 0.4 squared, you multiply that, you'll get that many Webers. And the only thing I guess I want to show here is if I change the orientation of that area, well, now I got to multiply by the cosine of theta. And kind of as a limiting case, which should make sense, is if you look right there, there's no magnetic field going through that area right now because the angle is 90 degrees, the cosine of 90 degrees is 0, right? And so magnetic flux, to a great extent, tells you how many magnetic field lines are going through my area. And I got, I guess, 4 right there, but if I increase the angle out to here, I'm only getting 2 of the ones drawn, that is. But that's a good way to think about magnetic flux. All right, let's stop sharing that, share back with you my PowerPoint, and make the transitions cleaner here, hopefully. So when we were talking about there, now I got the green border. So now it makes sense. Why did it not have the green border before? All right, come on. We talked about magnetic flux for the purpose of Gauss's law initially. And if you remember when we talked about electric flux, we said E dot dA, which was always back then when we were doing Gauss's law problems, always just E times A, because we picked an area so we didn't have to do an integral and that we didn't have to worry about that dot product. And it was just the charge enclosed divided by the permittivity of free space. And all that has to be is this charge is inside whatever closed area I drew right there. And I had to imagine that area such that the electric field was the electric field that was on that area. Okay, and so that area was like a probe surface. And now I want to talk about Gauss's law for magnetism. And we draw magnetic fields different from electric fields, because remember, if I had an electric field, I might have a positive charge, and let's see, which way is this going? Yeah, we'll do it this way, and a negative charge right here. The field lines actually start on the positive charge and end on the negative charge. So we get something like this for electric field lines. And we call that, of course, a dipole. And next to it, already drawn, was a magnetic dipole, where this is like the North Pole here, and this is like the South Pole. And the thing that is completely different between a magnetic and an electric dipole is what we said, these lines right here for a magnetic field are continuous. They don't start anywhere and end anywhere. They make continuous loops. And that's the reason why if I was to cut this thing right here, I would not just get a North Pole, I would get a new North and South Pole. I get 2 of them. I would get 2 new magnets out of that if I was to cut this thing and somehow wire it up so I could continue current going. And you know what we say there is, if I was to draw some closed surface, I don't know, sphere, there's every bit as many lines always going out of the surface as there are coming in, so that the net flux is zero. And that is the reason we say there's no such thing as a magnetic monopole. You can't isolate a North Pole like I could do right here. I could draw a surface around that positive charge, and there would be a net flux there because there are only field lines coming out of it. Whereas if I try to do the same thing around the North Pole of a magnet, there's just as many field lines coming in as going out. And so Gauss's law for magnetism is the law that says you can't isolate a North Pole, or conversely a South Pole, I guess, okay, because the net field lines passing through a closed surface is always zero. Gauss's law for magnetism is a statement of the fact that there's no such thing that we know of. Maybe this will change. We'll have to rewrite Gauss's law sometime in the future. But as of today, there's no such thing as a magnetic monopole. But flux again, okay? One of the things that we found is right here in that loop, there's an area. And so this magnet right here creates a flux through that loop, okay? And when the magnet moves, we see a current on a current sensor. And the current sensor people used back in Faraday's law were called galvanometers. And I showed you how a torque would be exerted on a loop of wire, and you hook a pointer onto that loop of wires, and you can see as you get current going through it, the galvanometer, the ammeter, it deflects. And so the thing we find is if the magnet is moving, we get a current. If the magnet is stationary, we get no current. And so what Faraday did, and Faraday's an interesting guy. If you ever get a chance to read about him, his claim to fame was that at, I guess, either Oxford or Cambridge, I forget which British school he was at, his mom was the cleaning lady. Okay, and Faraday was this young man, probably a little precocious as a kid, would go to work with his mom, and the professors kind of adopted him and taught him physics. Oddly enough, he had no formal math training. He was an experimental physicist who just made observations and did experiments, but he couldn't do the theoretical math work. But that's all we needed here. We needed somebody to realize that as this magnet moves, you get a current, and as the magnet is stationary, with the same magnetic field, there is no current, none measured, okay? And he kind of did enough experiments that he was able to see a pattern of why that is, okay? And here was another one of his experiments. When you close this switch right here, all of a sudden you create a big magnetic field. He saw that iron, which is one of those ferromagnetic materials, would cause a change in magnetic field in this magnet here, okay, which would cause a change in magnetic flux over here. And just as you close the switch, you get a current. But then once the switch was closed for a while, the magnetic field was steady again, no more current. And that's Faraday's observations as an experimental guy. Okay, so here's the law he came up with. And then I'll show you an example. If with my pictures there, it wasn't clear what he was observing, I got some pictures and an animation that hopefully will make this clear. What Faraday decides, and this is empirical, right? He doesn't have a theory behind this. He just says, hey, if you change the magnetic field, which means you're changing the magnetic flux through some loop, that produces an electromotive force. That produces an electric potential. Remember, electromotive force is that symbol we use, E, right? But it means some number of volts, okay? Some joules per coulomb. And of course, that is related to an electric field because remember, in the simplest case, where you just got two plates, one of them positive and one of them negative, and they're separated by some distance d, okay, the potential difference between the two plates is simply the electric field times that separation between the two plates, okay? And I'm drawing an electric field here. So changing a magnetic field produces, well, which changes the magnetic flux, produces an electromotive force, a voltage, which must have caused an electric field to be created. Now, the problem, of course, is which way does the current go? Which way is the electric field oriented? Which way is the electric potential difference? Is it, which side's the positive side? Which side's the negative side? And a guy named Lentz comes along afterwards, and he makes an empirical observation as well. And what he says is the induced electromotive force, the induced voltage, is always in a direction that opposes the original change in the flux, which caused the change, the EMF in the first place. Okay, and so we'll go through some examples of that. The first law can be stated mathematically. Voltage, electromotive force, number of volts, is equal to the rate of change of the magnetic flux with respect to time. And that's Faraday's empirical law. No calculus. He was thinking delta flux over delta time. Okay, that's all he was thinking about. He didn't know calculus. And the units, of course, are volts. And you can prove that because this is like a Tesla meter squared. This is over time, right? So I should write seconds here, shouldn't I? Seconds. Okay, let's see. A Tesla, we said, is a Newton per amp meter. Okay, let's see. And then I've got a meter squared. And then I got a second. And I need volts out of this. So what's a volt? A volt is a joule per coulomb, which is a Newton meter per coulomb. So let's see if we can get that. Well, pretty close right there. I got the Newton meter, don't I? Okay, so that's a joule. And then what's an ampere? That's a coulomb per second times a second. So sure enough, this is a Newton meter per coulomb, which is a volt. Okay, a joule per coulomb, which is a volt. So it works out. So we do get an electromotive force by changing the flux. I think Faraday had the mathematical wherewithal to have figured that out too. Lenz is the guy who writes this negative sign. He says whatever the change in the flux was, the electromotive force is going to be the opposite direction. Okay, and so I wouldn't take too seriously that negative sign. Find the magnitude of the electromotive force of the number of volts when you do one of these problems and you're trying to reason out these things, and then use Lenz's law to assign this negative sign based on a coordinate system or a right, left, up, down, into the page, out of the page kind of answer. And so that's Faraday's law. Pretty straightforward. If I give you the flux, find the derivative with respect to time. If you just know and assume it changes linearly, take the change in flux divided by the change in time. That'll also give you the electromotive force, the number of volts. All right, I want to jump out of this, stop sharing it, and stop sharing it. And instead, I want to share this guy. Yep, okay, that looked pretty smooth, I hope. Let's see. Yeah, and I'm going to go to my next one. Got to make it a little bigger for you. There, hopefully that makes it a little bigger. And this is what Faraday observed. And so if I take the north pole of this magnet and see, I bring it in, as it comes in, current deflected one way, but once I'm stationary, nothing happens. As I move it out, current change the other way, in, out, okay? And so what's happening here, I guess, there's a weak magnetic field right there. So there's a weak magnetic flux. As I move the magnet closer, the magnetic flux gets bigger. That's a change, okay? And as I pull it away, it's pretty strong right now. This makes it get weaker, and there's a change. And the current flowed so as to try to keep the original flux. It's almost like flux has momentum. And if you think about it that way, that's fairly helpful. Let's reverse the poles. I can do that with this little reverse button here. And you can see as I make the south pole come closer, that makes the flux being seen by that loop bigger. Okay, and while it's moving, you get a current deflection, and when I pull it away, you get exactly the opposite current direction. And so that's one of the experiments Faraday played with. He had a meter like this. He was able to make loops of wire, and he had permanent magnets, literally playing with magnets. All right, I want to show you the other one. Okay, and this is that other experiment that Faraday did. Go away. And so I've got a switch here. Right now, there is no current. That's the positive side. Current will go that way. Okay, you'll notice as soon as I flick the switch, watch the meter, okay, the current keeps flowing on this side, but once it's steady, the magnetic field is steady, there's no change in the flux seen by these coils over here, and you can see there's a multiplication effect here, right? A single coil, this time I got 1, 2, 3, 4, 5, 6, 7, 8, 9 coils, and you know the electromotive force which is generated must be more because I've effectively increased the area that's being changed for the flux. So let's open it, and you can see you change the magnetic field by stopping it, and a current formed as that happened. Once the magnetic field is gone away, okay, there is no longer any induced, and that's the word we use, induced current on this side. Of course, this device that I've made right here is a transformer. Okay, let me make sure that's, yeah. Let's do this one more, just so I don't have to change this thing. And one more time. And this is an interesting one because you can see I've got a magnetic field established, and that's into the page, the blue magnetic field. And I've got a little loop right here, and this is like a railroad track, and I got a bar running across it. And then across the railroad tracks here, somebody put a resistor. Kind of clever. And if you start moving the bar this way, okay, let's see, that would change the flux, I guess. It would be an increasing flux. And so a current flows as soon as I start moving the bar because I'm changing the flux seen by that loop, okay? And what you notice is there's a bunch of different ways we can change flux here. In the first place, I moved a magnet, a permanent magnet. In this, by the way, I could have moved the loop and kept the magnetic stationary. Your textbook refers to that as motional EMF, where you move a conductor through a magnetic field, as opposed to moving a magnetic field with a stationary conductor. In point of fact, we believe those two things are equivalent. We give a separate name to one. We call it motional EMF when the wire moves or when the bar moves, but they are exactly the same. We believe moving one is just a matter of coordinate system. I can see the coordinate system as moving with the magnet, or I can see the coordinate system as being stationary with the loop, as you wish. Okay. Any event, in this case, it was kind of an interesting way I chose to change the flux. I chose to change the flux by changing the area that the loop was. Right. It started off being a real small area, and as the bar moved, the area got bigger, the flux got bigger, and because of that, an electromotive force was developed, was induced, we say. All right, stop sharing those little animations. Hopefully come back right here to my PowerPoint. There we go. Share that instead. Hey, look, that was much smoother. I'm getting better at this. Let's talk a little bit about, there we go, about how I can change the flux. I sort of said this just a second ago. I left one off, right? In this top case here, I said the reason I'm changing the flux is because I'm changing the area that this conductor is seeing. In this case, I went to a smaller area by pulling on the coil and making its cross-sectional area smaller. Okay, so all of a sudden the flux through the coil is decreased. We didn't talk about this, but because flux has that cosine of theta here, okay, then if I have the loop initially oriented this way and I spin it, and so now it's oriented this way, I've gone from a maximum flux to zero flux. And if I continue spinning it, it would go back to maximum. And if I continued spinning it again, it would go to zero. And you may recognize that we call that a generator when we do that. We use some source of power, maybe it's steam from a turbine or water from a difference in height as a water wheel gets turns some sort of shaft, and we can spin this loop around, and we can actually create a variable electromotive force. I grew up in Buffalo, New York, near Niagara Falls. That was one of the central places in the country where this type of current and electromotive force was generated, because we had Niagara Falls with a big height change for the water. And after a while, people just figured, well, we just channel some of that water, which is falling down here through these turbines, make something rotate like a water wheel, and all of a sudden I can make a loop of wire spin, and we can generate electromotive force. We can generate voltages and then apply them to loads and have currents as well. So there's about 3 ways that I see it that you can change the flux. And the last one, I guess, is you change the field. And I said there's really 2 ways you can do that. You can either move the loop of wire in a stationary magnetic field, or you can move the magnetic field into a loop of wire. Either way would change the flux, and by changing the field strength seen by the loop. All right, a couple examples, I guess, and we'll pick up with some iClicker on Wednesday of these, but I just want to do a couple here. And in this particular case, I've got a rectangular loop right here, and the wire is got current in it. So let's see, and this is the thing about these Faraday's law, what's going to happen in this loop here. You've got to be able to figure out what this current, which starts the problem off, what magnetic field is that current creating, at least in direction. I mean, you could do the calculation, right? B is equal to mu 0 I divided by 2 pi R in order to figure out what the magnetic field is, say it's some radius R right there. You'll notice though, in this second loop, there's R right there at the inside, there's R right here at the outside. And so there's a variable magnetic field, which is getting weaker as you get further outside. But the big question is the magnetic field into the page or out of the page? And I'll give you a second to think about that. Put your thumb in the direction of the current, your fingers are swirling into the page right here. So everywhere around this, there must be a magnetic field into the page here. And I'll draw some outside as well. Okay, around a long wire like that. You can't forget what we did, 2 weeks ago and at the beginning of last week. There is a magnetic field like that into the page. Okay, and so in this particular case, the problem is that we're going to move this wire. I'm sorry, we're going to move the loop here towards the wire. So I'm going to take it and I'm going to move it, say, to there. And the question, I guess, is what happens to the flux? Well, hopefully you can see as I get closer to the wire from what I said, the magnetic field must increase. Okay, if the magnetic field increases, that must mean that the magnetic flux, I would need to know the area of the loop. I would need to know, I guess, its length and its width here. The flux also increases. I haven't changed the area in this particular case, but flux must increase. And so Faraday says there's going to be an electromotive force generated. Okay, there is going to be some current which is going to circulate around in this loop. The question is, does it go counterclockwise or does it go clockwise? And this is where Lentz comes in. Okay, so I guess the flux is increasing due to a magnetic field getting stronger into the page. Lentz says the result will be so as to oppose that. And so if it's getting stronger into the page, that would mean a magnetic field being created by the circulating current in this loop, which is out of the page. And the way to get that is to have the current go counterclockwise around this. Okay, that would create a magnetic field pointing towards me, pointing right towards my nose, which would oppose an increasing magnetic field into the page that is causing an increasing flux as I move this thing. So as I move that loop towards the wire, oops, wrong thing. I get a counterclockwise current, don't I? Okay, and you have to. When I tell people that, they go, "Oh, there's got to be an easier way." Dr. T, no way. You can't make me go through all those steps. And the answer is yes, I can. So increased magnetic field as I point it, increased magnetic flux. You need to oppose that. So I need a magnetic field which is going in the other direction that will cause this to go, to oppose that getting bigger. So opposite is what I'd say right here. And then the current causes counterclockwise is what will cause an opposite magnetic field. Okay, so it's about a 3-4 step logic path to get through to these things. All right, we're gonna do another one here. Again, this is more like that example I showed you where I got 2 railroad tracks. I got a magnetic field this time coming out of the paper, right? And let's see, as the bar drops, which it'll do due to gravity, for example, it must have a bigger area. Okay, a bigger area. So let's see, as the bar drops, say to here, same thing, the magnetic field hasn't changed, but the flux has, hasn't it? Because the area got bigger. So flux got bigger due to a magnetic field out of the page. Lenses, and so the question, of course, is the current going to go that way or is the current going to go that way? So let's see, if the magnetic field is getting bigger, the magnetic flux is getting bigger because of a magnetic field out of the page, current, according to Lenz, is going to flow so as to create a magnetic field into the page because that would oppose it. And so I guess that means it's going around in a clockwise sense, right? Because that would create a magnetic field into the page as opposed to the existing magnetic field, which is causing an increase in magnetic flux out of the page. Okay, so that must mean that the potential at A is bigger than the potential at B, okay, if the current is going that way because it's going clockwise around the loop. And so that now it asks you, well, which is higher in potential? Apparently point A is. Okay. Do another one here. This one's a little complicated, but it is a practical problem for older cars. I happen to have an old 78 Fiat Spider, which still has systems like this. It has a distributor, it has points, it has plugs, but this is how an ignition system used to work. This is the points and the distributor cap as you open and close a switch going to each of the cylinders. So I guess this switch closes And let's see, all of a sudden I get a current going other way. This current goes that way. So it comes over, creates a magnetic field this way, doesn't it? As soon as I shut that switch. And you got to kind of watch the way these coils are wound, right? Over the top is the direction current's going, so it's a magnetic field uh, going to the left. Well, just a second ago there was no magnetic field, but now all of a sudden I've got a magnetic flux due to a magnetic field to the left. What opposes that? Well, over here, you must have a magnetic field which opposes it going that direction, much like I had into, out of before. So that's the direction of the response. Um, I have to have a current flow. I have to have an electromotive force that's created to cause a current flow to have this induced magnetic field opposing the change. Okay, so let's see, in order to get a magnetic field that way, I think the current needs to come over the top of this loop around the back, over the top of that guy around the back, and then it has to go this way when it finally gets over to the spark plug. So for that period of time where this thing is closing, A must have the higher potential because current is going this way around the loop. All right, I think that's all. Yep, one more, I guess. In this case, I've got a current going that way. So that's creating a magnetic field into the page. And then this is an alternating current, and that means sometime later, the current flips around. And when that happens, this goes to coming out of the page. So that's your change from going into the page to going out of the page. That's the change that you see here. Okay, so I've got coming into the page, coming out of the page. The change is out of the page. Current is going to flow around this way because it was originally into the page. Current is going to flow, cause an electromotive force that will cause current to go this way around the loop because that'll restore the original field, which was into the page. And as it goes around here, if the current is flowing this way, clockwise around, that must mean that point A has the higher potential. Okay, and I think that's enough for now. I do want to do a couple math problems because I got about 6-7 minutes before I gotta leave and let you get on with your day. Here's kind of a simple problem somebody came up with, and I guess I've got this loop of wire right here, and I've got a magnetic field which is going to decay, and I've got it decaying exponentially in time. Well, hopefully you'll see here that makes sense because just about every magnetic field we came was proportional to a current. And if you remember from the RC circuits, which you may see again here shortly, current also decays exponentially in time, doesn't it? Minus T over RC. So it's kind of logical that if I have a RC circuit with current, which is decaying, of course, the time constant is just RC in those circuits. We saw that in last week's lab, that the current would decay exponentially, and therefore the magnetic field would decay exponentially. And so that's what I'm saying about this magnetic field right here. It's created by something, some kind of electromagnetic circuit that has a decaying current, which happens all the time in circuits like RC circuits. So over time, these magnetic field lines are going to shorten. Okay, and that means I guess the flux is going to change, right? There it is right there. That's the change in flux, or that is the flux as a function of time. And you can see as time elapses, this thing's going to go down because the exponential will decay, right? And just to remind you what a decaying exponential looks like, it's something like that for current. It's something like that for magnetic field, and it's something like that for magnetic flux. And the only question is, what is the flux? Well, it's the strength of that field. I'm assuming the field's constant, uniform across the area, times A, and so you can see that's how the flux is changing. Electromotive force then, electromotive force is that rate of change. And remember, don't take this negative sign too seriously here, but I got to take the derivative of that guy. Okay, well, the chain rule says the derivative of an exponential is just the exponential, but then I got to take the derivative of that thing, which brings down actually a minus 1 over tau. And just to make things look good, I just looked at magnitude. If you want, you could say I had that negative sign, and that negative sign, when I brought down the 1 over tau, I had them canceled. And so that is the electromotive force, though. Okay, that is the magnitude of the electromotive force. If I put a resistor in here, like I did, and I want to know the current in this loop, well, I just take that electromotive force using Ohm's law. I divide through by the current. So apparently the current over time is decaying exponentially with these factors out front, okay? And It's the time constant of the circuit. Whatever it was that created this exponential in the first place, maybe it's an RC circuit, that's how the current varies through this resistor right here. Interesting. Remember, we said we can change the flux by changing the field. That's what I'm doing in this case. I kept the area constant, and I kept the angle constant. All right, that's our first problem, I guess. Here's an interesting one. It's a linear generator, similar to the Hall effect that we talked about on our last class. So this bar started over here, and somebody pulled on it. And I guess I want to look at what happens here. This particular slide talks about what happens to a negative charge, but you could also look at it as what happens to a positive charge as this bar is pulled that way with some speed v. Remember, the force on these charges is equal to Q times V, there's V, crossed with the magnetic field. So we can use the right-hand rule to figure out, say, what's the direction of the force on this positive charge, or what's the direction of the force on the negative charge. Since the answer is shown here for the negative charge, let's just review. QV on a positive charge, field out of the page, my thumb is pointing downward. And so I expect this positive charge to be pushed that way. And so at the end of this bar moving through, there's going to be some positive charge here and some negative charge here. You can do the same thing with the negative charge. QV cross B, thumbs downward, but it's a negative charge, so it gets pushed upwards. When do the charges stop moving? Well, if there's a positive charge down here and negative charge here, you can see there's inside this bar an electric field which is upwards. Okay, the electric field which is upwards will cause the force on a negative charge to be downward. And at some point, we've seen things like this before, the magnetic force and the electric force on the electron, they're equal and they stop moving. But at that point, the electric force on an electron and the magnetic force on the electron, because the bar is moving, are equal. Cancel this, okay? And remember that the electric field is the potential difference across the ends of the bar divided by the length of the bar. Okay, that is an electric field, right? Volts per meter is also a unit of an electric field. That has to be equal to V times V. So I can find the potential across the ends of this bar right here, okay, as just the speed times the magnetic field times the length of the bar. This is formally called motional EMF, because I don't have a loop here, do I? There's no flux. I'm just going through an argument of forces and Newton's laws and figured out what the motional potential difference is, okay? And so as you were doing your reading here, this strictly, I don't see a flux here, but the magnetic field is causing a redistribution of charge, isn't it? By the way, this is real. If you were in an aircraft, and this could be the aluminum wings, which are conductive of the aircraft, as it moves through a magnetic field. Remember, in the upper hemisphere, the northern hemisphere, right at the equator, the magnetic field lines are parallel, but because the South Pole, which is at the Earth's geographic North Pole, is slightly below the surface, these guys are starting to curve downward. So if you're flying this way, you are seeing a downward component of a magnetic field. In the southern hemisphere, it would be upward, as shown here. So if you're flying either due north or due south, you actually do get a potential difference across the wingtips of an airplane, and it's measurable. Anyway, last problem here, and then we'll let you go. I could take this same bar that I just moved through a magnetic field, demonstrating motional EMF, and I could get more conventional with Faraday's law here, because I can take that same bar, I could put it on those railroad tracks we've been kind of hypothesizing today, put a resistor over here, and move the bar this way. Okay, so flux, field times area. Yeah, integral of B dot dA, but I can say I'm probably never going to make you do that. But you do have to recognize that cosine of the angle here, but that's all right, because the magnetic field is coming out of the page in this place, and the area is in the plane. So it's also, I can say, coming out of the page at us. So integral of B dot dA, I can ignore the integral, I can ignore the dot product. It's just B times A. And wherever possible, we'll make it be that. Now, realize, what is the area here? Okay, it is this length right here times this distance right here. Okay, and as I'm moving into the second position, initially it was only out to there, right? And so it's moved by some amount, which we'll call VDT, but I like to just see it as X here is changing, right? X there is changing. So the flux, B times L times X, L is now not the entire length of the bar, it's the length of the bar in between the railroad tracks, because that's where the current's going to go. That's where the charge is going to move to. That guy gets put right in there, and I realize the magnetic field's a constant. This dimension right here, the length of the bar in between the two railroad tracks, that's a constant. But yeah, X is changing as this bar gets pulled. And so let's see, I got just the derivative of X with respect to time, which I'm sure Professor Tech made you sure you understood was as is the velocity of the bar. Okay. And so just compare this application of Faraday's law as Faraday said it, rate of change of flux, to the motional EMF case, and you'll see they're both magnetic field times length times the speed, magnetic field times length times the speed. Same case, just viewed two different ways. All right, so again, if I want to get this current, okay, well, I have to take that electromotive force, that number of volts, divide through by that resistance right there, and that would be the current which is generated. Now, here's the big question. By Lenz's law, which way does it go? Well, we've kind of already decided which is the positive and the negative side of this thing from the previous example. In the previous example, I had positive at the bottom and negative at the top. And sure enough, I do here as well. And so this would be like a little battery where this is the positive side and it's going to go around to the negative side. The current is going to go around to the negative side. So I fully expect a clockwise current here, but let's see if Lenz's law makes sense. Okay, so initially I've got magnetic field out of the page and an area, which is getting bigger. And so I've got a magnetic field out of the page, and the flux which it's causing is getting bigger. Lenz's law says I'm going to get electromotive force. I'm going to get a current as a result of that electromotive force, and it's going to oppose that. So you have to create a magnetic field into the page to oppose the increasing flux due to a magnetic field out of the page. Well, which way would that be? That would be a current going clockwise around that loop. That would create a magnetic field into the page. And sure enough, it is clockwise around. And so this negative sign here, people are, is it positive or is it negative? I don't really care. In this case, the answer is clockwise, right? So the direction of the current is clockwise as we're viewing it here. Okay, I think that's where I want to end. We'll pick up on Wednesday with the power, the energy which is being generated as somebody moves this bar, because you can see in either case, in either this motional EMF case or in this railroad track case, the question I guess is, how do you make that velocity? Something has to pull on it. You know, I have a problem where a team of mules is pulling that bar across the railroad track. Okay, your hand might be pulling and grabbing it and pulling it across the track. That's necessary. Somebody has to apply a force right there, which means you're putting work into moving that bar. And then the question, I guess, is that work is causing current to flow. It's creating electric energy. How do those two things compare on a per time basis? So we'll look at the power which we put into it to move that bar, and we'll look at the electrical power which is generated as a result of moving that bar, and hopefully we'll see that energy is conserved here in the best case. All right, I think that's all I got for today, so I'll stop sharing here. And good news is I don't think I think I lost a couple people though. Any questions about the exam?
Dr. Tucholsky,
Yeah.
this isn't about the exam, but it's about worksheet 29.
Okay.
Is there any way you can help us or help me with a problem or two here, because I can't come to office hours at
Sure.
1 o'clock.
Yeah, sure. Yeah, and everybody else, if you don't want to hang around for that, go ahead. Yeah, I've got about an hour till my next class, so sure. Worksheet 29.
Yes.
All right.
Can I just ask a question first?
Sure.
Before you do that.
Go ahead.
About the exam, you said we have one attempt, as in
Well, you're gonna
question or
Yeah, so
per.
the question will pop up. I would work your solution on another piece of paper, type in your answer, and hit submit. I think if you change your mind, it's not going to give you, it's not going to tell you, hey, correct or incorrect. Okay. So if you go and you go, oh, that was wrong, I think you can go back and type over that question again. But that's an interesting question. If that happens to you and it won't let you go back in and type over that question, then you're gonna have to send it to me separately. Okay. If you
Okay.
Yeah, but my understand, it's a first for a lot of us. We're doing new things these days, but I think the answer is, Yeah, it's going to let you put it in once, and it should let you go back in and change it, but I can't guarantee that. All right, so make your best effort, your first effort, get the problem right. And that's probably about it. All right.
When is the test going live?
It'll go live to this evening. I want to give it one more look through before I make it go live. Currently it's scheduled 9:30, but I was going to, once I'm done with my office hours for my quantum mechanics class, I was going to make it go live shortly after that. So probably around dinner time tonight. And again, you've got till Wednesday morning, so you got all day tomorrow to work on it. All right.
All right, thank you.
You bet. All right, so we're looking at worksheet 29. And why don't I share the whiteboard here?
Okay.
Let's just go with that. And so which problem are we talking about?
So the front was fine, but
Okay.
Allison can't be here, but we were having problems with 3 and 4.
Okay, so here's what I think about 3, right? So there's that wire with current going that way, right?
Yeah.
And it's a wire, so what direction is gravity?
Down.
Okay. And let's see, which way is the magnetic field? Out of the page, right?
Right.
So what direction is the magnetic field on this wire? There's your current right there.
That would be.
Which way does it have to be? The problem kind of implies what direction it has to be, doesn't it?
Yes, that would have to be up then.
Have to be up. Check it with the right-hand rule, right?
Right.
Current's going that way. Magnetic field out of the page. My thumb's pointing up. Okay. So that's the direction of the magnetic field. And how big is that magnetic field? Well, we said I times whatever the length of the wire is times the magnetic field. Okay. And how big is this guy? M times G, right?
Right.
Apparently those two are equal. And so what do you have to find? What do you're figuring out what the mass is then, right?
Just M. So you would just set them equal. So.
Yeah. So you take that, divide it by G, that better be M, right?
Right. Okay.
Right.
Easy. Got
Second
that.
one. What do you got?
We got A. We just did that.
Okay.
The dipole moment vector was the current times the area. Would that be right?
Yep,
Okay.
exactly. So I got, and 5 times 10 to the minus 5 and
5.
amp meters squared. Okay. And why is that? Well, this is where people remember it's 1 millimeter by 1 millimeter is the size of this loop, right?
Right.
So that's going to make it a pretty small number of square meters. It's a real small loop. So remember, you're taking 1 times 10 to the minus 3rd meters, and you're squaring that to get the area. And 10 to the minus 3rd squared is about 10 to the minus 6, isn't it?
Yes, I think. Wait, 1, 2, 3. Oh, I think I did.
Counted the wrong number of zeros or something?
Yeah, so it should be to the
Okay.
negative 6.
Yeah,
Okay.
and then you multiply that, of course, times your field, times your current, and that gives you the dipole moment. And then you just did the cross product between the two.
Okay, so that's fine. And then for B, we did the torque equation is the magnetic dipole times B times the sine of the angle between them.
Okay, you can do it that way. That will get you the magnitude. But then you got to do right. It is a cross product, and so I think you really have to get a direction too. But yes, and what's the angle between them?
I thought it was not. We thought it was 90.
It is 90, right? Because the dipole moment vector would be this way, right? In the y direction. And it says the magnetic field is say I direction. Yeah, it's in the I direction.
Right.
So this is in the Y direction. This is in the X direction. There, and so that is a 90-degree angle right there. And so the question is the torque upward or is the torque downward, right? Because it's going to be one of those two. And it's mu. This is direction of mu. This is direction of B. So mu B, I think it's downward.
Downward?
Yeah, I think it's downward, right? Do the right-hand rule. First vector, second vector, thumbs pointing down.
First vector, second vector.
Yeah. So it's basically, you're doing J crossed I, right?
Right.
And J cross I, mathematicians tell us, is minus K. So that would be down, minus K, because the Z direction is up.
Okay.
All right. Now, what about the magnetic energy then? You're right on 90 degrees, but magnetic energy, U, is equal to minus mu. Oops, that's a lousy looking mu. Sorry.
Hmm.
Go away. Come on back. That minus mu dotted with B. And so where you use sine of theta for this one, right? What are you using for this guy?
The cosine of theta.
Cosine. And what's cosine? You said 90 degrees. It's still 90 degrees. What's the cosine of 90 degrees?
That was 0.
Yeah, so that must mean that C is 0, right?
Yeah, so we got
That's
that.
why you only get a real small angle right there, a real small amount of space to put that in because you can just see it's 0. Okay,
Right.
so now we're up to D. Now, if the loop is initially here and the magnetic field is there, don't you think it's going to rotate?
Can you say that
Eventually.
again?
Okay, so maybe my drawing isn't great here, but the loop is originally oriented so that it's pointing that way, right? Its dipole moment vector is pointing that way. The magnetic field is that way. And so
Mhm.
what I expect to happen to this thing is I expect it to rotate that way so that now this dipole moment is lining up with the magnetic field. So I expect sometime later, that's what the torque's going to do. It's going to make it rotate. And I think the magnetic field and the dipole moment vector will eventually be in the same direction.
Right.
Okay? And at that point, it will have the minimum potential energy, right? Because then the angle will be 0. Cosine of 0 is just 1. And so that's how much potential energy it'll have.
So the potential energy should then be equal to the torque.
Well, the number is, in terms of the value, it is, yes. The minimum potential energy does turn out to be that maximum torque in the number. But here's the thing about torque. Professor Tech should have told you that torque had units of Newton meters, right?
Mm-hmm.
Whereas energy has units of joules. But isn't a joule also a Newton times a meter? So it's the same number, but for energy, we say it's a joule. For torque, we leave it as a Newton times a meter. And the reason is we did the math a little different. This one was done with a cross product. This one was done with a dot product. When you do it with a dot product, you get energy, it's joules. When you do it with a cross product, like R cross F, you leave it as a Newton meter.
Okay.
All right.
All right. I think
So yeah,
that
the numeric values of B and C, though, I'm sorry, B and D are the same. I don't disagree. Although one's negative, right?
right. The D's negative.
Yeah.
Okay.
Yeah, that guy. All right.
Okay. Great. Thank you so much.
You bet.
All right. Bye.
Have a good one.
Can we go over part D on that problem again?
Part C?
D.
D. Part D. Hang on. Yeah. Okay. Let me erase some of this. Yeah. I don't need that problem at all, do I? It's tedious to do. There's probably a clear all. Yeah, there is right there. Clear it all. Clear all my drawings. That would have been a whole lot quicker. These are the things you learn in time. All right, so here's the picture, I guess. And initially, let's draw the z-axis. That's the z-axis. And I'll make this a little bigger here. There's the y-axis. And there's the x-axis. And that's the direction of the magnetic field, right? The magnetic field is that way. And maybe I should have different colors here. Format? Yeah, I do. Look at that. So I can draw. There's the magnetic field in red. Okay, now the loop is sitting right here. And the perpendicular to it is that way. So that's the direction of mu, right? And the angle right here is 90 degrees. So what I expect to happen is this thing's going to experience a torque, which is going to make this thing rotate that way. Okay? And like anything else, I guess, right now, you're going to experience a maximum torque. When it gets over here, the torque will go to 0. Okay, so this picture here will go to this picture. because this loop of wire has rotated around, and now the dipole moment vector is that way. And also, the magnetic field hasn't changed. We're assuming some kind of external magnetic field. That's a lousy looking straight line. There it is. That's a little better. The magnetic field is also that way. All right. There. So you got magnetic field, and see this originally, like when it's oriented like this, there's a tendency to make this loop of wire rotate around to there. That's what the torque is doing that you're calculating in part B. Good to go so far?
Yeah.
So now the question is, what's the potential energy right there? And what's the potential energy right here? Okay, I think the potential energy here, well, that's part C, right? Initially it's 0, okay? And the reason is because that's a 90-degree angle. Potential energy is equal to minus mu times B times the cosine of the angle in between them. Cosine of the angle in between them, that's cosine of 90, 0. But when this thing experiences a torque and rotates to the second position here, that's what's being asked about in D. That'll be the, that is the potential energy at when the dipoles align with the magnetic field. See, they're both aligned means in the same direction. And so now mu is equal to minus mu times B, again, times the cosine of the angle in between them. But now the angle in between them is 0 degrees, right? What's the cosine of 0?
1.
Yeah, so now the potential energy is just the product of these two things right here, right? And it's negative. So that does mean that from this state here, which I'm labeling number 1, to this state here that it rotates to, the potential energy has gone down, isn't it? Because minus mu B is less than 0. Any negative number is less than 0. So that's why it rotated from position 1 to position 2. It went to a lower potential energy. And so the minimum potential energy, I think, occurs when the angle is 0. It can't get any smaller, any more negative than minus mu B. Remember, cosine of theta here is a number that can be anywhere from minus 1 to 0 to plus 1, right? That's the range of cosine of theta. And so we're at the point where cosine of theta is as big as it can possibly be. So the potential energy is as negative as it can possibly be with the biggest negative magnitude. Does that make sense?
Yep.
So all you're really doing is multiplying mu and B, right? And putting a negative sign out in front. Whereas here you multiplied mu and B, but then you multiplied it by the cosine of 90, which is 0. And that's why you got 0.
Yeah.
All right?
Okay, thank you.
You bet. Probably more than you want. I probably could have done that in less time. You have a great day, though. Anybody else out there? All right. We'll stop this then. Nate, you're still there. Max, you're still there. Any questions? All
I'm
right.
working on number 2, but I guess I'm just trying to find the equation for that one.
Well, F is equal to IL cross B, right?
Yep, okay.
So did you get a number of newtons right there?
Not yet.
Okay, so just take the current times the length times the magnetic field. You'll get some number of newtons, and then pretend your first semester to get the acceleration divided by the mass, and then use one of the kinematics equation to get the velocity.
Got it. Yeah, it doesn't look too bad at all.
Yeah, once you got the force, then it's just a pretty easy first semester problem.
Yep. All right, thank you.
You bet.